Alright, I'm going to discuss how to find the sine of 15 degrees, and I want an exact value like you would memorize in a trig class. So, for instance, the sine of 60 degrees is the square root of 3 over 2. I want some kind of value like that for the sine of 15 degrees. I don't want the normal decimal answer that your calculator would give you. To get a value like this, you start with half of an equilateral triangle. You get a 30, 60, 90 degree triangle, and you can derive that value from the sides of that triangle. If you start with an equilateral triangle that has a unit side, then you find that the base down here is going to be half, because it's half of the 30, 60, 90 is half of the original equilateral triangle, and then you can use Pythagorean Theorem to determine that the height is the square root of 3/4. So in a similar fashion, I'm going to take this 30, 60, 90 triangle and cut it into two pieces using an angle bisector. So it cuts this 30 degrees into two 15-degree portions, and that's going to give me a 15, 75, 90 degree right triangle in this section here. All right, so I'm looking at this triangle that I've colored in yellow here, and so we know this height of this yellow triangle is square root of 3/4, and the segments down here I've designated as M and N, and you can see I've already filled in a value here, but we'll talk about how I get this value later. M and N are unknown. When we take the angle bisector, we do not get congruent sections on the opposite side of the triangle. So we need to derive M and N, and they're not congruent. The only way they would be congruent is if you started with the original equilateral triangle and that these two sides are congruent. So of the original triangle, we know that this side was a unit side. We know that this height here is square root of 3, so we need to find these two sections which add together to give us a half. So the term that we need to use is the Triangle Angle Bisector Theorem. And that's going to give me an equal proportion of 1 over the square root of 3 equals M over N. And so that's these original sides of the triangle in proportion to these two smaller segments. And it's this side over this side to this side over this side. So the two sides that are closest to each other are the ones that are being set equal to each other. So 1 and M, I have 1 and M, I have square root of 3 and N, square root of 3 and N. Another thing to notice is that this is two variables, and so those are kind of difficult to solve for. So we can look at the equivalency of 1/2 equal to M plus N. That's these segments added together are going to give us this half. And we can solve for either N or we can solve for M and then substitute it into this. What we're going to do is, since we're interested in N, we are going to keep the N here and substitute in a value for M. So we're going to use this value here. So we have this setup. 1 over the square root of 3/4 is going to be equal to 1/2 minus N divided by N. And now we need to solve this equal proportion for N. And that's going to take a little bit of algebra, but it can be done. And so the first thing to do would be to cross multiply, and that'll give us N equals 1/2 times the square root of 3/4 minus the square root of 3/4 times N. Next, we will add 3/4 N to both sides, and so we get this term of 1 plus square root of 3/4 as the coefficient of N, and then we still have this term over here. So we're going to divide this term from both sides, and you can start to do a simplification of this fraction by multiplying the top and bottom by the radical conjugate of this denominator. So since we had a plus here, we're going to rewrite that with a negative here, top and bottom, so that this is an equivalent fraction. When you multiply across these denominators, this is a double distribution, or FOIL if you like that term. On the numerators, it's just a distributive property. So when I multiply this term by the 1, I have the same term. When I multiply this term by square root of 3/4, I get 3/8. And then when I multiply these two together, I'm going to get 1 minus 3/4. And then I have a further simplification. This is just working through the algebra. I subtract these two terms. These terms can't be subtracted, but what I did do as a simplification is I took this quarter and I did take the square root of it, so it brought a half outside the square root sign, so I had a half times a half, gave me a quarter on the outside of the square root now, and left just the 3 inside. So I have a quarter times the square root of 3 minus 3/8 divided by a quarter. And then, if you notice, each of these have a term of 4 in it. I multiplied top and bottom both by 4, so it gave me another equivalent fraction of some numerator over 1, which simplifies to this term. So the square root of 3 minus 3/2 is the value that I had for n up here originally. And then I'm going to take that value along with the square root of 3/4, and I'm going to put them into the Pythagorean theorem. And so that's what I have going on over here to the side. So using the Pythagorean theorem, I'm going to square the term that I just got. I'm going to add it to the square root of 3/4, which was the original height of the triangle, and solve for this unknown hypotenuse. Looking at just this first term, we need to remember that this is it's itself multiplied by itself. So this is, again, a double distribution, or you can think of it as FOIL. So I'm multiplying this term by this term to get this term by this term to get this. Square root of 3 times the square root of 3 is just 3. And then the square root of 3 times negative 3/2 is this term. These two terms can be added together, which gives you a doubling of this, which means that the denominator's lost here. These two terms can be added together, and that gives us the 21 over 4, and then we're adding that negative 3 square root of 3 here. We need to remember that we have the plus 3/4 square root of 3/4 squared here, and we have the h squared here. We need to add those terms in. When I square these, since these are opposite operations, I get the 3/4 here that I'm adding into this term, and I'm taking the square root of all of this and the square root of this side so that I get h by itself. I have two fractions in here with same denominators, so those can be combined together. And then once I do that combination, I see that I have a 24, a 12, and a 4 here. So this is a reducible fraction, so I reduce that fraction here. So this is my hypotenuse. I already found the base of that triangle, and the base of that triangle is the side opposite of 15 degrees. So I have what I need here. The sine of 15 degrees is the opposite over the hypotenuse. So I'm going to take this term and put it in the numerator, this term, and I put it into the denominator. And when I go to my calculator and I check this, I find that, if you can see this here, I type in that value and I get 0.258819045. That continues on, and it's irrational. If I now do the sine of 15 degrees, I get that same term. So I have shown with the calculator that the term that I've gotten is in fact the term that the calculator will agree with. It just doesn't look like a calculator answer. And some of you may find ways to simplify this algebraically, but I've essentially determined what it is I was going to show. I have the entire triangle now filled in. So I know this hypotenuse, I know this base, and I know this height. So I've derived the 1575 90-degree special right triangle theorem. And so any triangle that has these angle measures in it is going to be in the same proportion due to similarity. So this can be scaled up or down as needed to apply to those triangles. And so we've created another set of terms, special trig terms, that give us an exact answer. Hopefully this has been helpful in seeing how to derive these trig terms where you get precise answers instead of decimal estimates. You can use a pentagon or possibly other shapes to be able to generate these trig terms. When you use a pentagon, you get two special triangle theorems out of that one polygon. And there's another nice feature in the pentagon when you do these derivations. Cheerful calculations.